Hey, welcome to section 8.3 in Applied Math. Today we're going to talk about mass. So first of all, I want to tell you what page I'm on. If you want to follow along in your book, you can always do that. I'm on page 454. On page 454, and you can always read a little bit up on any of these things in the book or on YouTube. But I think the book does a pretty good job of having a readable text so that you can hear more of the discussion around the topic than just the examples. So anyway, I just want to read you just a little blurb out of the book on page 454 that tells you that weight and mass are not the same thing. And you can see weight does not equal mass. Weight is going to be the pull of gravity, and mass is the amount of matter there is. So they're actually different. So weight and mass are not the same. Mass is a measure of the amount of matter in an object. It is determined by the molecular structure of an object, and it will not change from place to place. Weight, on the other hand, is the measure of the gravitational pull of an object on an object. For example, we know on the moon, people that we think it's weightless, it's actually 1/6 as much pull on the moon. So there is some pull, but it's a lot less. So we would not weigh very much on the moon, but we'd still have our mass with us. So thus a person on the moon weighs about 1/6 as much as on the earth, even though the person's mass remains the same. In space, where there is no gravity, a person has no weight, but does have their mass. Even on Earth, the gravitational pull will vary from point to point. The closer you are to the Earth's center, the greater the gravitational pull. Thus, a person weighs very slightly less on a mountain than in a nearby valley. Because the mass of an object does not vary with location, scientists generally use mass rather than weight. Although weight and mass are not the same, on Earth they are proportional to each other. The greater the weight, the greater the mass. Therefore, for our purposes, we'll treat them the same. But I just wanted to be clear that they are different, so it didn't seem like I was telling, a mistruth here, misrepresented it. I wanted to make that clear. But we'll sort of act like they're the same because they are proportional for our measures. It's going to be okay. All right. So with that said, we're moving into the metric measure gram. Gram is our basic unit of measure for how much something weighs, or its mass. But like I said, we'll go ahead and just call it weight. So to demonstrate how much a gram weighs, I've brought a paper clip. I don't know if you can see this, but oh my goodness, it's very light. A paper clip, that's about the weight of a gram. So it's a very tiny measure, even in its unit, basic unit that we use to convert from. So remember from our previous lessons that we put prefixes in front of our basic units, and so our basic unit of mass or weight here, gram, we add prefixes. So if we go up the scale, that's 10 times that, so 10 grams, so 10 paper clips, if you can visualize that, would be a decagram, a DAG. Then we have hecto. We don't use these measures very much. You don't hear that very much, hectogram. But that would be 100 of these paper clips, a hectogram. And then we hear this one though, kilo, a kilogram. So a kilogram is about 2.2 pounds. And a pound isn't a whole lot either. So even at kilo, the 1,000 grams, we still don't have a very heavy measure. Now as we go down the scale, we add our prefixes like deci, a decigram, a DG, centigram, a CG, and milligram. There's another one that you hear used a lot, milligram, like in medical field, something very tiny measure for medicine. A milligram would be 1,000. So if you took that paper clip and cut it up into 1,000 little pieces, you're just almost microscopic there, but that would be a milligram, what a milligram weighs. So that's our idea there. To get our mind around. Oh, and then there's one more. If we added 3 more places, or actually go up 3 more places up, 1,000 kilograms, we would be at a metric ton. Now it's spelled a little different, T-O-N-N-E. A metric ton actually is very close to our Old English customary ton that we think of in the American system. So it's about the same, but it's actually just a little bit more. So if you took 1,000 kilograms, 1,000, which would be about 2.2 pounds, so it'd be about 2,200 pounds, right? And our Old English ton is 2,000 pounds, so it's just 200 more over that, 200 more pounds over that. So it's very similar, but a little bit heavier than our regular English ton. All right, so the first thing you do on page 455, if you're following through the examples, it'll ask you kind of to analyze what measurement makes the most sense. So in example 1, it says choose the appropriate unit. Now, there's no absolute right answer because you can measure in any unit you want, and that's okay, but which one seems like the most accurate? If you're measuring a large thing, a really large thing, ton, something you'd normally measure in pounds, maybe in kilograms, and something super tiny in milligrams. So they go through this and they say, which unit would you probably use to measure the weight of a 1-year-old child? So if you were measuring a child, you'd measure in what we normally measure pounds. Actually, we usually measure our weight in pounds, so kilogram would be the unit most like that. B part, if you were measuring the weight of a whale's going to weigh a whole bunch, right? You can measure it in anything, but probably ton, because it's just so big. Ton might be how many tons is a whale. C, a pair of glasses. You know, my glasses are real lightweight, so we might be able to measure it in something smaller. So that's, again, a judgment call, but maybe in grams. Again, you can measure in anything you want, but it would be most likely, because it's certainly not a pound, but it would be part of a pound. It would be less than a pound in kilograms. So maybe gram might make sense there, and so on. So sort of just get your brain going on how much things weigh and how much these weigh, kind of to analyze that. All right, on the next page, we go back through a chart that we saw in the last section where we talked about a cubic centimeter. 1 cubic centimeter, so that's a 3-dimensional figure. If you think of a cube, I don't know if you've ever drawn these, but if you draw a box or some little cube like a dice, 1 centimeter in width, height, and length. So length times width times height. It doesn't matter which one you call which, but when you multiply the 3 dimensions of a box together, length times width times height, that is the volume. And if each side were 1 centimeter, 1 centimeter times 1 centimeter times 1 centimeter, when you multiply, you get 1 times 1 times 1 is 1, then centimeter to the first times centimeter to the first times centimeter to the first. We learned an exponent rule that said when you multiply sort of like variables, which in this case we could think of that as being the variable, we add the exponent, so 1 plus 1 plus 1 would make to the third. So this would be, the volume of this would be 1 cubic centimeter. So 3-dimensional space, 3-dimensional unit here, 1 cubic centimeter. Well, and this was on that last section, we learned that a cc, another way of calling that is a cc, a cubic centimeter, if we filled that box in with water, it would hold 1 milliliter of water. So an ml is the same measure in liquid measure. And then we're going to add one thing onto it in this section, which is how much would that weigh? If we measured it, it would weigh a gram. So 1 cc of water, if you measured it, it weighs about the same as your paperclip. Very, very light measure. All right, and then we can also derive some other measures that are equal. A cubic decimeter holds a liter of water. Again, these were in the last section, but we're adding on how much does that weigh, and that is a kilogram. If you weighed a liter of, like your liter of pop should weigh about a kilogram, about 2.2 pounds. And then 1 cubic meter holds a kiloliter of water, and then that weighs 1 metric ton, 1 metric ton. All right, so that would be the end of our charting, things, conversions that you need to remember as we've been going through this chapter. All right, so let's work a problem. Example 2, the volume of a fish tank. So it says we've got a fish tank that is 1 meter long, 50 centimeters tall, or the height, and then 250 millimeters wide. And then we're asked to determine how many liters that holds. Determine that in liters. And then the next part, B part, is how much kilograms would that be? How much would it weigh in kilograms? So we got 2 parts there. All right, so first of all, we need to convert it to some sort of three-dimensional measure. So we're going to take the length times width times height, just like I mentioned with our cube or any box. The volume would be just multiply the three dimensions, length times width times height. Well, they're in different units though, meter, centimeter, and millimeter, so I have to fix that. And it's really up to you which unit you go with. I want to follow the book example and convert them all to meters. So I'm going to leave that one alone. But centimeters needs to be converted to meters, and millimeters needs to be converted to meters. Now remember, from a previous section, we have a chart that says our basic units of measure, meter, liter, and gram. So any one of those that you're converting, here we're converting the meter. Then we add the prefixes deca, hecto, and kilo. And then down the scale, deci, centa, and milli. Those are our main players that we convert from. When we're converting just first degree, just regular linear units, we move one place on this chart. So to convert from centimeter to meter, we're going from centa up to base meter is 1, 2 up. When I move up, I move the decimal to the left. So again, up the scale moves the decimal to the left. 2 places from centa to meter. So the decimal points at the end at right now 50 centimeters, so 2 left makes it 0.50 or 0.5 meters. Converting my millimeters, 250 millimeters to meters. So we're going from millimeters, so right here, millimeter, and we're going up to meter. That's 1, 2, 3 places. 3 places up the scale means 3 places left. Right now the decimal's at the end, so that'd be 1, 2, 3. So 0.250 or 0.25. Now they're all in meters. You know, this one was already in meters, 1 meter long, 0.5 meters high, and 0.25 meters wide. Multiply 1 meter times 0.5 meters times 0.25 meters. Take out your calculator, do that calculation. You should come out with 0.125 meter times meter would be meters to the third. So that's in cubic meters. Now notice that the question asks us to determine the amount of liters. So right now it's in cubic meters. So which one, I've erased my little chart now, but you all hopefully wrote that down. But back to your chart we had earlier, that converts to kiloliters. A cubic meter is the same thing as a kiloliter. So right now it's in kiloliters. 0.125 cubic meters is 0.125 kiloliters. That's how much water would fit inside of that tank. All right, so we need it in liters. So right now we're at 0.125 in kiloliters. And our question A says how many liters is that? Now we know how to do that from our moving on the scale thing here. We're back to first degree. You know, it wasn't third degree, but we have that chart that tells us cubic meters is the same thing as kiloliters. So we were able to get out of the cubic units and get over to something linear, kiloliter to the first. Regular kiloliter. Now we're back to our scale. To get from kiloliter to liter, kilo is up here, so 1, 2, 3, we're going down this time. When we go down the scale, we move the decimal to the right. So to the right, 1, 2, 3 places. That's answer A, 125 liters of water for that fish tank. In question B, it says, well, how much does that weigh? This would be liquid measure, the liters of water it held. Well, how much does that weigh? Again, that little chart we just wrote down, we had a little chart that said, if you're in kiloliters, that's in tons. So, I'm sorry, I'm in liters. If I were in kiloliters, though, the scale says ton. But in liters, again, look across your scale. It says a liter and a kilogram. They're a direct conversion. That every liter weighs a kilogram. So 125 liters, it's an exact conversion because they're straight across from each other. And every liter is a kilogram. They're exactly the same. A liter, every liter weighs a kilogram, so exactly the same. So that's our answer here, 125 kilograms. That's how much that would weigh. They could ask us, well, how many grams is that? How many tons is that? And we could do the conversion on the scale, but that is exactly what they asked for, so no conversion needed there, just knowledge of our scale.